All right, so I hope you have learned how to do that. This will become, remember, I already set up these things here for you. So it's from 0 to 4. X goes from 0 to 4. Y goes from 0 to the square root of 16 minus x squared. And of course, you have 1 and then dy dx. The first part, oh yeah, by the way, this is what I wanted you to do. And you can see it's a lot more complicated than what you saw here in the first place. But if you want to do this, okay, so you know this becomes square root of 16 minus x squared dx. Do you know how to do this? Yeah, there is a formula that you can use. You can do a trigonometric substitution, or you can just go directly to the integral table. Remember the table of integrals? And you can find a form that involves the square root of something minus something squared. And you should be able to do that. And so that's possible. But remember, I mean, this is a lot more complicated than what we did simply in double integral in polar coordinates. Okay, all right, let's go to the next problem. I want you to find, and by the way, all the theoretical part, this is the only theoretical part of this we're going to do. So after this, I will do several more problems in polar, just so you can get used to double integrals in polar coordinates, all right? So I want you to find, this time, the double integral over r of f dA, where f, r theta, is, oh, okay, sorry. I'm going to give you this rectangular coordinate system, rectangular function. Right? F of xy is simply x, right? And then my region is the upper half circle, right? Of 2, radius 2. Okay, and so this is my region, and so that's my region here. Okay, let's see if you can integrate this using polar. Find that, and then we will come back. Well, let's see. Yeah, let's go ahead and do this together. Okay, and so the first thing is you have to set this up. All right, now remember, you have to have r d theta. So that means you have to decide what theta is and what r is. So what is theta in this case? Well, you can see theta goes from 0 to pi, right? And then r goes from 0 to 2, okay? Because here's 0 and then 2, and and you go in all kinds of directions where theta is between 0 and pi. So this will be from 0 to, not 2 pi, sorry, 2 pi would be the entire circle, 0 to pi, 0 to 2, and then, ooh, I can't write x anymore, right? So what do I have to write? In terms of r theta, x is r cosine theta. So r cosine theta, right? And then what? The a, ooh, I have to have that r. Where did that come from? Yes, of course it came from dA in polar coordinates, right? And I will emphasize that over and over again because I do not want you to forget that r, okay? That r will always come in when you use the polar coordinates. So notice here I have two r's, right? And so that is, you can go ahead and take the integral. And if you want to, you can pause this and watch how this develops later. Since you have r squared here, the first, you get 1/3 r cubed. Okay, now you have cosine of theta here, but that can be written before or after this. Let's go ahead and handle this part as r goes from 0 to 2. Okay, and then you still have the theta here. Okay, so what I just did is to take care of this first part, and this will give you, now what is 2 to the third? That's 8/3, right? And then you have from 0 to pi of cosine theta d theta. All right, and then you have 8/3, and then what's the antiderivative of cosine? Of course, it's always been sine, and it will always be sine of theta. Right, and then you do this, and of course, that's easy because the sine of pi is 0, sine of 0 is 0. The answer is 0. Whoa, whoa, whoa. Is that right? Is there any reason to believe that the answer should have been 0 in the first place without doing any calculations? Look at r, and I think it's pretty obvious, right? So once you see this, you say, oh, duh, okay, because you look at this x, okay, this side x is positive, and this side x is negative, okay, and I mean this is exactly what I was talking about in symmetry. This is a function which looks exactly the opposite in the two sides, the left-hand side and the right-hand side. So one side cancels the other one because the picture in R is completely symmetric. It's clear that this function as an odd function will cancel each other, and the answer would be 0 in the first place. And you didn't actually have to do that if you knew what was happening. But it's good to know, and it's good that we got 0, because I would be very worried if I did not get 0 over here. All right, let's go to the next section, or not next section, but next subsection within 5.3. You know, you learned about polar functions. Okay, what are the polar functions? Okay, instead of y as a function of x, here r is a function of theta. You remember this, right? So you had things like, you know, you had things that looks like this, or that's called a cardioid. You had things that make a little circle here like this, you know, and these are called limosons, or and have different names on there. Sometimes you have spirals. Sometimes you have these things that looks, and this is also a cardioid. You also had, you know, these leaves, you know, or maybe 4 of these, or maybe 12 of these, or 2 of these, right? These are called petals, or roses. Sometimes you have a 4-leaf rose here, and all of these could happen, right? And let me give you an example here. If you have r is equal to 6 cosine theta, do you remember how to sketch the function here? All right, so let's try to, you know, practice this. Right? And this is just one example, but these are all examples of polar functions, by the way. And these are the graphs, and there are many other graphs of polar functions. If you remember your calculus or pre-calculus class, maybe you have done a bunch of these, and maybe your instructor, like I do, say sometimes it's important to stop and smell the roses. It's good for your heart. Okay. All right. So there are a couple of ways to think about this. You can do an old-fashioned, you know, table like this, theta and r. Okay. But the way I prefer you to think about this, or the way I prefer that you think about in terms of a problem like this is try to think of starting at 0. Okay. So cosine of 0 is of course 1. So this one starts at 6. Okay, when theta is 0, which is this direction. And as theta goes from 0 to pi over 2, which is here, what is the cosine of pi over 2? It's 0, right? So as you go from here to this angle, 0 to pi over 2, the value of the function r goes from 6 down to 0 in a nice, smooth way, right? And maybe you can try to figure this out at some place like this, which is a pi over 3. A cosine of pi over 3 is 1/2. So at this point, it's like 3, which is much shorter than 6, right? And you can sort of think that this is going to be like this. And by the time you reach pi over 2, it's 0, right? And then it starts to become negative. And so it becomes like this. And this will actually be a circle, right? So think of what happens as theta grows. Okay, now I am not spending a lot of time here to graph these functions. That's what you did back in the pre-calculus or a trigonometry class or something. At this point, I want you to be able to, you know, figure this out, right? So how do you do that? Well, when you're given a question like this, maybe you remember this. Try to find r square and expressions like r cosine of theta. So here, I can multiply both sides by r. Okay, so this becomes r squared is 6r cosine theta. And this will tell you what it's supposed to be. X squared plus y squared is equal to 6 times. Remember what this is, right? It's just x, right? And so this now becomes this equation. And you know what to do after this, right? Yeah, you complete the square. And actually, I broke. Something happened here. All right, so once you straighten this out here, you can add 9 to both sides, right? And that's completing the square. and it tells you exactly what the graph is supposed to be. Of course, it's a circle of radius 3 centered at 3, 0. Okay, so hopefully you remember some of these things. You don't have to know everything that, that you learned. You don't have to go back and study this entire chapter or anything, right? But I do want you to be familiar with this because sometimes you do need to know what the graph looks like, all right? So here's an example of a problem that you may have to do, okay? So this would say something like, find the area. Let me go ahead and write the whole problem down. All right, so the question is, find the area bounded by the graph of this function, 3 times cosine of 3 theta. All right, do you have any idea what it looks like? Well, well, maybe not, maybe you do. Okay, so let's try to at least sketch a little portion of this. Okay, that way we can maybe use symmetry or something, right? So let's say when theta is 0, cosine of 0 is 1 multiplied by 3, so that's 3, starts here, right? And let's see what happens when, does it look like pi over 6 here? When theta is pi over 6, 3 theta is already pi over 2. Cosine of pi over 2 is 0. So between this and this, between 0 and pi over 6, r goes very quickly from 3 down to 0. So it becomes somewhat like this, right? So maybe I should say when theta is between 0 and pi over 6, r goes from, you don't have to write all the details here, 3 down to 0, okay? And then what happens in the next 30 degrees? Then from pi over 6 to pi over 3, r goes from 0 to, now what happens is between pi over 6 and pi over 3, if you multiply these values by 3, then the 3 theta goes from pi over 2 to pi, right? So that's when the cosine is negative. So it goes from 0 to negative 3. So how would you describe that? Well, from here to here, it'll be negative, right? And so in order to describe that, I mean, this goes from 0 to negative 3, right? And maybe you get the idea at this point, right? And then so on. If you, and then by the way, for the next, let's see, for the next 90, or for the next 30 degrees or next pi over 6, the cosine will still be negative, but then it goes down back from negative 3 to 0. So it'll go back like this, right? And so you can go ahead and try to figure this out, but maybe you get the idea. You may have been really good at this. And at this point, I will just go ahead and try to tell you what happens here. This is also becomes 3 and then goes back to 0. And then from here to here, it's going to be back in here, right? And then the second time around, from theta goes from pi to 2 pi, it'll just repeat the same thing, all right? And so this is called a Mitsubishi sign. No, it doesn't. It's not called that. It's called the 3-petal, not pedal, 3-petal rose, or 3-leaf rose, or whatever, okay? And so that's fine, all right? So now the question is, now I think it's easy to visualize what's happening. Find the area bounded by the graph of this. Basically, we need to find the area of what? Of all 3 of these. But see, all these 3 are exactly the same size and shape. These are congruent, right? So the area, the entire area is actually what? 3 times one of these petals, right? But each petal is also symmetric. So why don't we just find, let me just, here. Why don't we just find this area here, okay? And so this area, let's call this R0, okay? So it's the area, the entire area is 6 times the area of R0, which is 1/6 of the entire area, right? Okay, so we can do this, right? Let's go ahead and find that. R0 is the area where theta goes from 0 to pi over 6. Okay, and then R goes from 0 to, of course, you know, where, I mean, where this ray hits this particular graph, which is 3 cosine 3 theta, right? So that's what we have working for us. Okay, let me go ahead and rewrite this again. All right, so the entire area of the region bounded by the graph of this function is 6 times half of each leaf, which is from 0 to pi over 6, and then from 0 to 3 cosine 3 theta, right? And then the area is, of course, just dA, but dA is r dr d theta, right? Yeah, that's what we have. Now it's going to be a little complicated. I don't want to give you a, by the way, you're integrating one, you know, because you're looking for the area, but this is just the A. And if you want to, you can just put one, because that's the definition of the area. All right, and so this gets a little complicated because the first thing you do is you have to have r squared divided by 2, and then you have to substitute this whole thing, right? And sometimes the problem can become a little nasty. I try not to give you many different trigonometric functions here, but occasionally, you know, this happens. And by the way, let's take the 2 out. So this is going to make that into a 3. All right, and then we will say this is 9 cosine square 3 theta d theta. You okay with this? Right. So this will be 27 times the integral of cosine square 3 theta d theta. All right. Now, yeah. So if you may have to go back and look at your trigonometric, you know, integrals again. Hopefully you are not going to have to do it too much. But do you remember how you integrate cosine square? Yeah, it may help you to rewrite this as this part as 1/2 of 1 plus cosine of 6 theta, right? And so this is based on the double angle formula. And then cosine, so what I guess what I'm trying to say is here, I am using, let me go back because I think I should be explaining this, okay? So anytime you see cosine square alpha, you should write this as 1 plus cosine 2 alpha all over 2. Okay, so this is one of those the formulas that came from a double angle formula of cosine. Okay, so basically I'm saying what you learned is that cosine of 2 alpha happens to be 2 cosine square alpha minus 1. And from that, you get this equation. All right, so I think this helps you figure out how to get the answer here. In fact, you can just take out 2 in the denominator. Okay, and like I said, I try to take as many denominators, as many constants out as possible at every single moment. And so this 1 just becomes theta, and then plus cosine of 6 theta, that is going to be sine of 6 theta divided by 1/6, right? Does that make sense? Yeah, I mean, the thing is, you want to do a quick check by differentiating this. Theta becomes 1. So remember, 2 is already been moved out, right? So theta, if you differentiate this with respect to theta, it becomes 1. And this, if you differentiate this using the chain rule, it becomes 1/6 times cosine of 6 theta times 6. And so the 6 will cancel, giving you cosine of 6 theta, right? So that is the correct integration. And so you still have 27 over 2, and then you have pi over 6 plus 1/6 times sine of 6 times pi over 6. That's sine of pi, and that's 0, right? And of course, when you substitute 0 here, it becomes 0 plus 0, so you don't really have to worry about that, right? So the answer turns out to be, well, let's see, you can also do a little cancellation here. This becomes, you know, these are all going here. This is 2, and I'm dividing this by 3. You get 9, so it's 9 over 4 times pi. that is the sum of the areas of all three leaves together. Okay, I know it's a little challenging, especially when you have a function that is you haven't integrated for a while, but I think this is something that you should be able to figure out. Okay, I have a couple more examples I'd like to show you so you can be well prepared to do your homework. All right, so I'm going to give you a question, and then I will stop this part and then go to the next part. But before you go to part 3 of this lecture, you should at least set this up and maybe even solve this question for yourself. All right. So here's a question. Let's say you have, that looks really ugly. Let's try to make it a little nicer. You have a hemisphere. Okay. You have a top hemisphere. All right. So you have, so let me give you this question here. Find the volume. And in fact, I will pause it and then I will write the whole thing down. Okay, so the question here is this. I want you to find the volume of the hemisphere, and here's the hemisphere of radius 4, okay, from which a cylinder of radius 1 is drilled out from the middle. Right? So you take a tool and you drill out this radius 1, basically the diameter 2, cylinder out of this. So you have this thing that's hollowed, okay? So it's a hemisphere, except the middle part is being taken out, drilled out, and you have this thing that sort of looks like, I don't know, molding for a cake or something, right? Try to find the volume of this. Now, it looks like a hard question, and you may panic looking at this, all right? But promise, it's not going to be a hard question, all right? Try to set up the double integral in polar coordinates, y polar, well, because the region will be very circular, and then try to find the answer, all right? And once you think you find the answer, you can come back and finish this lecture and go to part 3.